Should I start?
Yes.
Yeah. So our project was a mixture of like Wasserstein Coresets and data mixtures. So like we read some papers on this. Next. He hasn't. We tried to contact. We tried to contact him. He hasn't responded to us. Yeah. No, he has not contacted us. Yeah. So next slide. Huh. So the paper I'm presenting, the main motivation for this paper was like training. When the LLMs we train, so they have mini batches. So what we try to do is that we want mini batches so that the convergence is fast. But due to the large number of mini batches, this is infeasible because it requires large GPU memory. So what we try to do is that match the gradient of the large mini batches to the random batches. But this is infeasible due to highly imbalanced mixture of sources and language data. So some sources like have large number of examples in the data, and some sources have few examples. So that causes an imbalance, and due to which there are some problems. Then the Adam optimizer. So I'll talk later about how Adam optimizer causes a problem here, and also the gradient. So the gradient which we calculate for the LLMs, it has very large dimensions, and so it is like very complex to cater. So an example is shown here. Like for the Phi 2 model with batch size 128, it requires 44 GB of GPU memory to train for just 2.7 billion parameters. So with Adam optimizer. So the recent memory efficient techniques for LLM fine tuning use methods like finding smaller parameter sets using low rank like LoRa, and despite these innovations, they fail to achieve the performance, uh, and they have large training time. Next slide. So a potential solution for this is standard gradient matching. So in this method, we try to select some medoids. Medoids are like representations, like like there are large number of samples. So we try to choose central points from them, which are called medoids, so that they represent the data, and so we can have a smaller representation of the big data set. So for that we have medoids. So this method, the standard gradient matching method, had good results for image classification tasks, but for LLM fine tuning, it has poor performance, and this is due to the three things which I talked earlier, uh, which are the highly imbalanced sources, the Adam optimizer problem, and the and so also the large gradient size, dimension size. Okay, so for dealing with the imbalance in language data problem, the issue is that, like I told, some sources have large number of examples and some sources have small number of examples. So for this, so when we try to select medoids for these for this imbalanced data set, uh, majorly we get those medoids which are from the big sources, and the small sources are not taken into consideration much. So this causes an imbalance. So this causes an underrepresentation for the uh, of the small sources, and so the model performance is not good. Next. So, oh sorry. Uh, Back. Okay. Huh. Yes, this is a paper. Uh, yeah, I'll share the paper with you. Uh, so, so next slide. So to deal with this problem, we the theory in the paper is that so So instead of using medoids for the small sources, we use all the examples of the small sources, so that the medoid problem is not there. So we give because already they are small, so we can give all the examples, and that doesn't cause much problem. And for the bigger sources, we use medoids because that essentially captures uh, the the distribution of those examples. And also we use uniform weighting, so that there is a balance across both the small sources and so basically the big data sets is the big data sets are also like spread across, like they have huh? Yeah, so we can partition them, and for each partition medoids can be selected very with good performance. Data mixtures, so Wasserstein and data mixtures we do.
But the goal is not necessarily data mixtures. I mean, they're coming from the point of view of efficiency, memory.
Yeah, Coresets applied for data mixtures.
But data mixture is not the only goal, right?
Yeah, so what they can sampling from
Yes, but at the level of cache composition, you're trying to mini batches, right?
Yeah.
In a manner that is reflective of core sets, but the goal is not just data mixtures.
Yeah.
Otherwise, like, if it's data mixture, then here they have a rule of fiat, right? The rule is basically that if you have small, then all examples are.
Yeah.
All data mixtures, they don't have these rules by fiat. We learn. So it's not the main goal.
yeah.
Yeah.
In our project, we have sort of tried to work
That may be right. Right. However, my honest opinion is competition is good as a right. I think data mixture is a more useful problem. How much compute will you save also? Some competition is certainly. I think the critical is delivering data mixture. But fine, this paper has slightly different goal.
Yeah. So for the Adam optimizer problem, the problem was that the vanilla gradient method uses raw gradients, but the Adam updates use normalized gradients. So this is the formula based on which the Adam optimizer normalizes the gradients. And to deal with this, we need to uh, like match the normalization of the Adam optimizer to the data set which we are using, and so in this way we deal with that problem. This is also the formula. So this is the formula used to calculate the medoids for the big data sets. Next slide. So now the third problem, which was the higher gradient dimensions. There is a curse of dimensionality, which uh, um, I'm not very sure. So they are. I'm not very sure at this point. Yeah.
So what are might be so MD or PT or no, it's not. It's the exclusion moving out.
That's standard.
Standard, yeah. But what are trying to do is like.
So using this, we are trying to find the best possible medoids, inculcating the Adam optimizer normalization. Yeah.
So instead of a naive gradient matching, we are trying to match the Adam
optimizers normalization
update.
Yeah. So the curse of dimensionality. So what this is exactly that when the gradient dimension is very large, so the distance between the gradient vectors becomes nearly uniform. So we are not able to differentiate properly that the various distances between the vectors, and in that, so that causes a problem in finding the midpoints. So what we want is that a smoother lower dimensional gradient estimate that preserves the essential signal. So for this we use two methods. One is the gradient estimation using SPSA. So this is the formula. So in this, basically, instead of using full back propagation, we estimate the gradient, so that problem is not there. And the second method is using last V projection parameter. So this is basically a thing used in LoRa, and so in LoRa we calculate the V projection parameters, and using the last one, basically it is the just before the final output. So basically we have reduced the gradients much. Next.
SPSA, how is it? So it's basically, instead of back propagation, you're just looking at difference.
Yeah.
Okay, so that is an approximation to the partial derivative.
Yes.
And the perturbation that you talked about, sometimes perturbation.
Yes.
That is only for the last V projection parameter.
So, it happens here. So for the last V projection parameters, so basically there are multiple V projection matrices, and so the last one is just before the final output, which the model gives, and so it has a fewer number of dimensions. So that helps us in reducing that. Take it next. So, and the even if the V projection gradients are high dimensional, then the last thing which we can do is sparsification. So basically making a lot of things zero, and so taking the top edge dimensions, basically like projecting it, and so it finally gives us a smooth representation and improved midpoint selection and memory efficiency also. And so for the experiments, these were the this was the setup. So we used the data sets and the models 5.2, 5.3, and so these are the training details and the baselines and the evaluation data. So the results are like the CoLM model method introduced in this paper outperformed all the other methods. Next slide, Eva. So as we can see that in all the models, the CoLM performed best. Here it with the least mini batch size, it could get the best results. The memory requirements have reduced, and the variance has reduced, and number of training iterations, in lesser number of iterations, it got the best results. And here also we can compare time, accuracy, and memory. It performs best in all.
Yeah, I mean, these kinds of results are also very scary. See, ultimately, people, there's no free lunch. There's always a trade-off. The paper doesn't. What is the trade-off they're presenting?
No, I don't think they have shown that. Next. And this is also like in all the cases, the CoLM performs the best.
Yes. Is there any critique you have in terms of the trade-off? I mean, for example, they say for small classes they use all the points, but how small a class? That's also hyperparameter. If the class is less than 5 instances, 6 instances, that's 5 hyperparameter.
Yeah.
And if I set that to be arbitrarily large, and obviously performance will degrade.
Yeah.
Another performance is speed will degrade. I don't have midpoint anymore, and I'm actually considering all the points from most classes.
Yeah.
So there's no trade. I mean, is there a critique? You use your own critique, right? That's why they are encouraging to critique.
Yeah, the critique is just that they haven't.
But you didn't talk about it.
Yeah, it's okay. Okay.
Is there no other critique? Fueled by my critique? Is there some other critique you have that comes to your mind?
Not yet.
There would have just some black magic in the way you're choosing your hyperparameter. I don't know the ETA that all the parameters and Adam same update will hold here or not. That's also critique, right? Adam made some assumptions, suppose somewhat motivated by accelerated gradient descent. But now in the process of gradient matching, See, this is what your critic should do. In the process of gradient matching, or I'm adding update matching, I'm slowing things down even more. I'm actually adding more momentum. I'm adding a little bit more momentum. The matching is a momentum addition. So won't it actually further slow things in further slow the greediness of the otherwise gradient descent? You understand my point? Now you're only agreeing on my critiques. You have to have your own critique also. See. So this is my critique, or if you don't agree, that's also fine. Okay. So have your critique. Go. So the effort score is basically parameter change. Model learns each sample. It's projecting parameter changes. It's just projecting the parameter change. It doesn't yet. Oh, this is not using Adam. It's just yeah, but they don't use Adam at all. Can you go back to the previous slide? The previous one? Yeah. So, they say task specific fine tune of LLMs. That's the goal. So the pre-training could have been using some Adam optimizer, but they are discarding all of that. They're saying the fine tuning will be based on only a vanilla gradient descent. Yeah. Okay. And that too using a small model. The importance was using a small model to calculate the importance across gradient. Because we can't use the large model. But even for the fine tuning, this is only for fine tuning. I didn't understand. So you have pre-trained a large model, and you're using a small model to measure. Not clear. What is the large model doing? What's the small model doing? So we are fine tuning using a large model. So this is for you are fine tuning a large model. That's something using a large model. Yeah, we are fine tuning a large model on a larger data set. Right. So what is the small model doing? Importance score using small model. So we need to for Coreset selection we are using first the small model to calculate the importance scores across the data. The small model is pre-trained on the same large data set as the large model is no. It's from the same family. Same family is okay. Which that you are on. No, it's not trained on the fine tuning. It's a black box. Yeah. Somehow trained. You don't know which data set is trained. Assuming that the model is the same. Yeah. If that is different than the data set. We are fine tuning on a completely new data. But the proximity is being trained on from scratch. It says we use to calculate the importance. So basically, you're saying there's some assumption that the paper is making that because they are from the same family, the small model reflects importance scores, reflects the data sets. It's probably trained on similar data proportions. Somewhere there's some similarity which is unarticulated. That is big. So I think you should get curious. No, it's straight from scratch. It's already trained. It's already trained. Pre-trained small model. A pre-trained small model is used to estimate the importance scores for examples for fine-tuning, which are going to be used by large model. Now, the fact that this carries forward to fine-tuning of the large model is under assumption that there are either data distributions are similar in that is used for pre-training the small and large models, right? So when you say K regions, you mean you just sort those norms and then bucket into K regions?
Yes, so that we get representation from each of those regions. And from each of
So again, it's not clear. Verify importance of regions on target LLM. That means you have to really do a fine tuning. What does verification mean? What is ST? I'm not explaining what is ST.
ST is the score calculated by the target. This is the score calculated by the
So you're saying ST is the target. Target means the main
model.
the one SS is the.
That's one.
So you can get this verification result only when you also you have to fine tune the target LLM.
No, we are only verifying the importance, so this is based on a few.
So the deal after the million form and the Singh
No, it was not.
So it's only a sample on some sample set of the points you are verifying, not on all the points. It's not clear anywhere. I mean, you are expecting us to kind of extrapolate and understand where is it mentioned on a small set of points.
he is for that.
Yeah, so we divide B is each of those K beings.
Okay. But the K regions, you're not taking all points from those K regions. Is that
We
right?
are sampling points. Each of those
Why is that not mentioned anywhere? Sampling is not there anywhere. Yeah. Allocate more selection budget regions important to target LLM. So based on the importance score.
So first, we begin with the initial budget for all these speculative score is by the small model and verification score is by the large model.
So basically, each one is calculating the variance norm of the smaller one. That's the ratio of the other. So what are the issues of the block?
So I think it's just calibrating this. It is calibrating the speculative score against the verification score, right? So the speculative score seems to be very different, and the trend is the distribution is different. Then you have a problem. They show that well, they seem to agree, and the verification score is which is actually used in practice too. And that doesn't matter. Data regions are very. I mean, he's saying that. So they are not sorted. They are not sorted.
Yeah, because we did the verification once we had the data is sorted from the computer.
Okay.
So yeah, this was the experimental setup. We used data sets from Aryan and then various other data sets. And the models were used from the same family. For example, Lemma 7B was used along Lemma 2B and then corresponding lambda system models. And these were the various baseline techniques that we use, ECS and TB. Yeah, so we also vary the pooling rate from 20% to 90%, and the staff outperform across all those techniques for different. So we are fine-tuning for fine-tuning, we are tuning the data set across different rates. So higher rate means we are using less time to tune the data set. So yeah, we wanted to see how it performs across different speeds. As in data, we use to tune the data set, not the model parameters. No, the data set.
Only data set. This is only data. Go ahead.
Yeah, so yeah, staff had a higher score than all those various methods. Next. The efficiency was also higher. It showed an improvement about 60 to 70% by reducing time to be about 3 hours compared to 11 and 9 hours for treatment solution. Coming on to our project proposal, so the two papers that we analyzed based on we kind of sort of a hybrid of both those papers. So we have proposed a hybrid source of speculative selection for Coreset selection. For this, we have combined the speculative selection algorithm of staff to the source-aware training methods of OLM. Next, so this is our proposed methodology. We start with source identification. So for this, we use data sets like Sinkhorn, file, and other like medical and legal niche data sets. And first of the source identification, which is if we have the label data sets, then we use those labels. If the labels are not there, then we use for the data sets that from the internet, like the Sinkhorn, we use keyword heuristics and URL based matching for labeling them. And for the other data regions, we use clustering and to label them into PS. The first step is the source identification. Second is again, inspired by staff, use a smaller model to calculate the importance score The second step is what we thought of is that we'll do an uncertainty estimation, which we will use a simple feed-forward model to calculate the uncertainty of the various embodied scores that we've got, and then sort of rank them across each of the data systems. So with the supervision, sorry, what is supervision? What will be that? See, this supervision is a aspect whether the model is whether the sources are there. How would you do that? So we will based on temperature of the model, we are using
Continue.
Yeah, I think there was one good presentation of traditional skills. So you can discuss it with about.
My only thing is scope your proposal so that focus is more on data mixing than speed up. And I think the speed up thing after a point will come back to us if you don't do the right data mixing.
Yeah. So what we were aiming to do is that there are certain reasons which gets left out in case of methods like staff because the speculative model may not have a good certainty of getting the model score. So we do an uncertainty estimation and then we rank those samples according to their uncertainty in those various reasons, and then we verify using the larger algorithm only on focusing on those uncertainty. So we sample 70% of the uncertainty and 30% is random sampling. And then we calculate the score using linear regression for both the speculative and target element scores. And then we allocate budgets. So budget is allocated. First, we allocate minimum threshold budget for all the various data regions. Then the budget regions are inflated based on their sizes, different sizes. And then if the size and the score of a certain region falls below a certain hyperparameter threshold, then we inflate the budget for that.
Okay. We can move on. Any questions? Who's the next lead? Thanks.